All right, let's get started here. So here I have James. He's currently a senior solutions architect at NVIDIA, and he works with companies to design, deploy, and develop their AI systems on the edge or in the data center. He previously was a team lead at Patriot One Technologies, where he designed and deployed many different kinds of AI and ML systems. And he's here today to discuss bringing an AI system from proof of concept all the way to deployment. Take it away, James.
Thank you so much, Bintu. And thank you everyone for attending today's workshop on bringing an AI system from the lab to deployment. As Bintu mentioned, my name is James Cameron, and I'm currently a Senior Solutions Architect at NVIDIA. That means that I'm a forward deployed engineer that embeds as a specialized technical resource with NVIDIA's customers. I have a specialization in AI and ML systems, specifically around the end-to-end deployment pipeline. Before NVIDIA, I worked as a lead engineer at Patriot One Technologies, where I was responsible for all aspects of deploying ML systems. We had many successful deployments, but just as many analytics never made it off the ground into the field in any long-term capacity. This hands-on workshop is going to cover my hard-learned tips and techniques for bringing a model fresh from the data science bench and into an active deployment. The high-level agenda will take us from the first few steps of getting the proof of concept of deployment going, next to building a field-ready deployment. We will be sure to cover some optimizations that are often needed for meeting requirements of a production system, like latency and throughput. And finally, we will cover quickly some larger topics to ensure complete coverage going forward, moving a deployment from a one-time project to a repeatable process. As we go along, my colleague Caleb Smith will be moderating the chat and may stop me if there's anything that he thinks should be answered immediately. Otherwise, we will collect some questions and there will be a final time for questions and answers. I'll be stepping through some code examples as we go along. I have made this code available on GitHub if you would like to follow along or revisit it after the talk is over. The link's just at the bottom below here. I realize it's a bit of a lengthy piece to type back into your browser, but I promise it'll be worth it, and I will flash it up on the screen as we go to the particular code parts. So with all that started and done, let's begin. And I'll reminisce briefly on my first deployment. I was working with computer vision, so I wanted to deploy a segmentation algorithm. So I used mask-RCNN, and it was just running on my laptop. So every first deployment has to start with a model. My first model was fine-tuned with an internal data set, which we had collected, and then we tested on data we had collected from a live field exercise. So we had set up surveillance cameras, and people had walked around, and we collected the live feeds. Before starting with a deployment process, we'll need to verify our model with data that actually looks like the model, looks like what the data the model will see in production. Your model could be using an online corpus of text and then sample data from interactions you had for customer, just as an example. We then want to ensure we have buy-in from our business stakeholders and customers that this model will meet their need. However, a standalone model doesn't really capture people's imagination. So in order to better understand how we should be using the model, we should create a simple proof of concept deployment to better understand how we use the model. And the point I really want to drive home with this first model building and deployment is that the data set used in the data science lab for training and even the validation data set is often a walled garden. When your model hits your first unprepared data in production, you'll quickly find this. You'll have many problems and challenges, whether it's simple missing or unformatted values in a tabular data set or something completely unexpected. Um, you'll have a wide variety of experiences. I personally had experienced this when we were working with surveillance data through a closed circuit television system. But we have been working through the images captured in the day, but at night when the lights were off, we would have the system switch to infrared vision, something completely different than an image of full color during the day. So it would look from a beautiful scene to suddenly ghosts and of people walking around. Regardless of your domain, moving a model into production for everyday use is a job unto itself. And in fact, the industry, as many of us know, has coined a term for this: machine learning engineering. And it's a very new term. I think it originated in the past 3 to 4 years. And from then has only become more refined and standardized, but it's nowhere near complete. The ML engineering can be an individual or a team responsibility. Everyone needs to understand the role the AI model is playing in the system. For example, it could be the back engineer adding recordable metrics for the data science team to view in real time in deployment. It could be the DevOps team creating CI/CD pipelines for model testing and deployment. The main takeaway here is that adding AI or machine learning components to the system requires many of the same actions as other system components, but with a different lens. A single individual can be responsible for many facets of AI and machine learning engineering. My overall recommendation is that regardless of having an individual responsible, the key is to having everyone involved and informed and aware of the parts of the AI and ML system that you are incorporating into your overall product or business. In the same way a slow database results in poor user experience, the whole development team needs to work with AI ML systems in mind to avoid the pitfalls that can form if ignored. And I suggest the best way to find a lot of these pitfalls as a team is to iterate the deployment of your AI ML system, starting with my first deployment. And so we want to figure out with a first deployment that the model being proposed to use in the field has the correct inputs and outputs. Model always starts with its data, so your system will need to too. Whether it's images, text, or anything else, your system will need to ingest it. Taking the data and pre-processing it into the format the model expects, which is the next step. This could be several individual functions or multiple functions. Uh, Oftentimes in a computer vision model, we'll expect a resized, normalized image, while with NLP tasks, the words need to be tokenized before being processed by the main model. And classical ML models, you'll need to extract the features before running inference, which is the next step. Inference is where the magic happens. The data is processed and the results are returned. This is the black box that everyone talks about. Often it's a single call, just .predict, and the results are then returned and need to be often processed, so post-processed into something like business rule, simple if-else statement, or more complex function like non-max suppression. However, this final step should really take the output of the model and put it into something that the rest of the system can use and digest. In the case of a first deployment, we can talk about the standard flow used for ML models like we just laid out, but the tools can vary wildly. For the first proofs of concept, I'd suggest sticking with the simplest way of building things. Your model was likely developed with Python, stick with that. Then the toolkit you use for training can also be used for inference. So if you're using PyTorch or TensorFlow or Scikit, just use the framework. And then wrap it in a simple UI to show the concept off to your stakeholders. So allow the user to upload an image or type a sentence. It lets the user better understand what is being built. And from this proof of concept, you may learn that the output being displayed isn't as useful as you thought it was. A bounding box may need to become a segmentation mask, or text may need to be an audio output. You may even learn that the inputs selected aren't what your stakeholders have to give. You may think that the stakeholders have video and they only have images. So let's step through the first notebook of this workshop. Again, link just quickly the link at the bottom of where the code is, and I'll open up my Jupyter notebook. So a simple deployment using a simple model. Stony Brook University developed a model called DM count, and it's used for crowd counting. So in this notebook, we're going to start by cloning this repository, which I have already done, so it should error out here. And then next we have, just restart the kernel. First, let's import the model into Torch, and by downloading it from a Google Drive, loading it in to CUDA memory, it's actually a VGG19 based model. And so we're going to load the state dictionary, evaluate it, and then push it to our compute device, which I'm using a GPU today. We're then going to declare an inference function. So pretty simply, we're going to have a target input width and height for the image. We're going to resize it, do our pre-processing, do inference with PyTorch, move the results back to the CPU, and then post-process them with a crowd count. So we'll have a count displayed of how many people are within the image, and then a heat map overlay to show where the people are located generally within the image. And this will be returned back to the user interface. So Grad.io is an excellent tool for building very simple UIs, just to demonstrate proof of concepts. And so you can declare quickly your inputs and outputs. So you can see here that we're specifying a image as an input, and our outputs are an image with an overlaid heat map of crowd density as well as a predicted count. And you can see I put some example images. So let's quickly look at the user interface here. I'm going to select this crowd image here, and we're going to submit it. And love live demos; they always can go so well. We're going to see we have a heat map here of where the people are located in the image and an approximate predicted count. Just to demonstrate when there's nobody involved, we're going to have a count of 0 and no predicted heat map. So this is a very simple deployment example to get buy-in from your stakeholders. So now that we move to our first actual deployment. We've built a proof of concept and implemented the feedback we received from your stakeholders. So whether that means a new model has been trained or a whole new concept has been designed, or perhaps we leave it on the whiteboard where it needs to be, we now have the buy-in from stakeholders and businesses and customers to do our actual first deployment, which means sticking the system in production and leaving it out in the wild for a bit. So the scope of work to build our deployment will go up significantly here. There are many questions that will arise, many questions. Many do not have immediate answers. Online or offline processing. Do we have streaming data coming at my system from a sensor? Or am I periodically running database queries and processing the data? Where is the deployment going to live? Is it in the cloud, the edge, or maybe both if processing has to be done in a hybrid manner? Do I have latency targets I have to hit? Throughput targets? How much data am I processing and how frequently is a question that you'll have to answer. Which and how many models am I serving? Is it 2, 1? Is it 10? What hardware should I use? Lots and lots of questions will come up. And so I recommend sticking to just thinking about what is the system's goal. This should be the driving motivation when answering all these questions. Our application will drive latency and throughput requirements where the system is deployed and more. So let's walk through some examples to demonstrate. An autonomous vehicle, such as a sidewalk sweeper, are going to need to respond as fast as possible to events happening around. So whether that be someone walking in front of it or a car going by it, we want to make sure that it responds in a real-time fashion. So low latency, real-time data ingestion are a must-have. This ultra low latency requirement also translates into real constraints around where the computer hardware is required, leading to we need to have embedded edge compute. We don't have time to send back to a central data server. Finally, there are multiple perception models that are used for self-driving, segmentation, detection, so multiple models will be running concurrently and across multiple sensors. On a different end of it, let's say we want to monitor our new social media platform for moderation. Assuming our platform is successful, big if there, we will need to have high throughput to process all of the content being published. We can rely on batch processing since the moderation doesn't need to be instantaneous. And finally, we are likely to look at cloud-based processing since that's where our application will live and we want to increase or decrease depending on system load. Again, as users log in or off the system. In another direction, we can consider a medical application using machine learning models to detect fractures in an X-ray scan. Obviously, we don't want to have false negatives or false positives, so high accuracy is required. However, we don't need the high throughput or the low latency of the previous examples, but we do need to worry about data sovereignty since it's patient data. And this means we'll need to ensure the data is stored properly and processed in a data center within the control of the hospital to meet regulations and other concerns. So despite several widely varying applications, there are high-level commonalities between all of these. One of the key things that need to be considered is meeting system constraints. So that's usually the three usual suspects of latency, throughput, and cost, often interconnected. Measuring system utilization is critical in determining how your system is doing. Depending on your requirements, the system utilization can inform what hardware you require. For instance, if you see your hardware at 100% and you still need lower latency, you should consider moving to a larger piece of computing hardware or further optimizing your system. You'll want to constantly monitor and improve your models for production use. By updating your models in a live environment to increase accuracy, it will be consideration for your system. And finally, the ML system architecture is a commonality. So as we spoke before, it fits as the data comes in and passes through. So a common AI system diagram is, as I said before, data ingestion is the commonality. So however, data ingestion will change depending on what system you're building. There are many questions that you'll arise. Is the data streaming from a sensor in a real-time manner, like the autonomous vehicle, or is it triggered periodically by an API call? This ingested data will feed to model inference. Data in, results, and actions out. Inference is lumped together here across one or many models. Also, this data could move between devices depending on compute resources. And finally, there's these results or actions that are created, but the model need to be, finally, these results or actions that are created from the model that need to be passed on to the rest of the application, whether that's saving the results to a database or streaming an overlay of an image to the UI. And so while data ingestion and results handling can vary wildly, model inference is very similar no matter what data is being ingested or what results are being handled. Inference serving is the way in which AI models are deployed. Ideally, it's a centralized module or component for model inference. Using a single service or process to handle all model inference can have many benefits. Saving memory and I/O resources, having the same configuration, interface, and endpoint for different models can reduce development time. We can go another level by hosting multiple models for all use cases. For a visual example, let's say we have a client application with two different models being requested, each with one overlapping model, both model B in both cases. So by moving to a single service, which is doing the inference, we gain the synergy of not needing to redeclare the model in memory. We also can lump these pieces, these calls together from different applications across the model to get something called dynamic batching, which we'll cover a little bit more in later, a bit later in the presentation. When we're looking at different inference serving technologies, there are often an abundance of features that may or may not be useful. So my favorite list here, having access to model store is particularly useful for an inference server to give you control around loading and unloading models. Having multiple models versions load at the same time can be very beneficial for development. Dynamic batching, as I just talked about briefly, is having multiple requests to the same model come in at the same time and then having them batch together to increase computational efficiency. And batching is something we'll explore in detail later. When multiple models are being used, ensembling them into a single call for your inference pipeline makes life easier. Instead of having your application call for every individual preprocess inference call, it's just one call to the model, your results are returned to your application. The less calls to the inference server means less data movement, which reduces load and latency. Another really critical note is letting data scientists work with the tools they prefer is always best practice. Having multiple ML frameworks supported like PyTorch and TensorFlow prevents unnecessarily difficult conversations about how you can only deploy one of the two. Being able to write custom code in plain languages for execution inside the inference server is also super useful when you just want to wrap a brand new AI framework that hasn't been optimized or adapted yet into your infrastructure. And you'll see I hammer this point in quite a bit. Having metrics for inference latency, failures, and more are much needed insight into your AI application and prevents you from having to create these metrics yourself. So let's jump into an example to show serving. So next notebook. So in this example, I've created a centralized model serving application with NVIDIA's Triton inference server. And so to begin, we're going to load in the model as we had before. So we're going to first load in the model as we had before, load in the PyTorch model. And then we're going to do something a bit different. We're going to deploy or export the model into an inference framework known as Onyx. And Onyx is one of the many formats you can use for deployment. So we're going to specify the target input and height for the model, give it a dummy input, and then pass it to Torch's Onyx export function to create a Onyx model. So we're gonna let that run quickly. And then I've already set up Triton, so this is all running inside a Docker Compose network. And we're going to use Docker Compose to orchestrate the notebooks with Triton Inference Server. And this has been done in the back end. And if you go into the repo, you'll see how it's been kind of created. So Triton Inference Server has been turned on and spun up in something called poll mode, which means if we copy in a model into the directory, it will automatically load in the model and get it ready for inferencing. So we can query that the model has been there and how it's being seen by connecting to it via gRPC or HTTP. I've chosen gRPC for this instance. So this client will connect and we can get the configuration of the model being set. So we can see that, we have a max batch size of 4 set. We have an input of, 3 channels RGB, 800 by 1280 height width, and then our output sizes that we use. Some more pieces here. See that we're using the Onyx runtime as a backend in Triton Inference Server. So now, just as we did in the previous example, we can create an infer function, which just specifies, passing the input name as is said in the config, and then telling the declaring the input name, the shape, and the data type, setting the inputs from our NumPy image that has been passed, and then getting our outputs and passing them back to the main function. Again, this detect crowd function I modified from the previous example. And so Basically, same thing here as before, pre-processing. Our inference is now the infer function from above instead of the dot predict from PyTorch, or the forward from PyTorch. Uh, and we're going to just declare it back in the grad.io backend as we did last time. And so this should just spin up, and you really shouldn't notice a difference when I click this application and show it to you. So let's just refresh here. Click another image, submit, and you'll see that just like last time, we get inferences. So simple example of using an inference server and making calls are quite similar. You can probably see the appeal of having a similar interface for different backends like TensorFlow or PyTorch or Onyx, which can be very nice. So let's get back to the main presentation and continue talking. So now that we've talked about how best to run AI models with inference serving, I want to also talk about profiling your AI models. So testing and isolation your models, not for accuracy, but to see how inference leverages the various parts of your compute hardware. We have simple tools that give you a single value that describes usage. That could be, like filling it with top or htop if you want to look at CPU usage and memory usage, but NVIDIA SMI for GPU usage. So you have simple pieces like utilization as a percentage, memory usage. You can see in this case, I took a screenshot when my computer wasn't doing anything. So this is often enough to quickly understand where you're at in terms of using all the hardware you may have available to you. There's also many more very complex tools. These tools will give you timelines which correspond to computing instructions that make up your model. This will give you a detailed understanding of what features of your computer you're leveraging. This is very important level of detail, which will help especially later when you're doing very deep optimizations. So your timeline, so this was from NVIDIA's Nsight profiling tools. And you can see here, you can see the different instructions being computed when on what device, and you can see what functions calling it. Like you see Python here is processing and handling CUDA free and a lot of other calls to the GPU. So when you're in the field, you'll need to monitor your system's performance. So this could be many different things, but some highlights are pre-infer processing latencies to see if there's any spikes, queue count latency to ensure that all clients are getting the results returned in a timely fashion, number of models being used and how often they're being used through an inference count, system device memory usage, to see if you have any memory leaks. Those are always good to find. Compute device usage, make sure that you're always operating that 100% and using everything as much as you can. But one of the most important things I want to mention is you'll want to monitor your accuracy in the field. So you should monitor this, and you won't just get, you don't in the field, typically you don't get results whether your model was right or wrong per se. You're going to be looking at metrics like the number of low confidence results. So let's say your average class accuracy was at 90%, and suddenly you get a dip to 30%. You may want to store that data, perhaps maybe phone it home so your data scientists can collect it, use it potentially in further trainings, or use it as a data point in which to generate or create more data to improve going forward. And you may even want to alert your data scientists for each time this happens. So just another quick example, I'll walk through another notebook here. We have a notebook just to demonstrate metrics. So let me just refresh here. So Grafana's are really, Prometheus and Grafana are like a fairly well-known stack for showing real-time stats from your system. So I have a couple of systems already outputting statistics. A DCGM, or a data center graphics card monitor, basically will export information about your GPU usage, like power, temperature, clocks, utilization. You can see I haven't used anything quite yet. That will spike later. And you also can get information from Triton about successful DM count runs and DM count compute time and DM count latency time for how long it takes in a queue to process. So these are all really useful stats to get, but let's quickly use the Prometheus client in Python to declare a new statistic that we'll use. So the new statistic will be just a quick detection confidence. So here we set detection confidence saying, a description of detection confidence for the model, and we can use different labels for different detection confidences. So we can record how each class has different accuracy, and which is very important. So we're going to start.
Hey, James, your audio is off right now. Hmm. 1 second, y'all. Now talk.
Oh, am I back now?
Yep, you're back now.
Okay, how long was I out?
A solid minute.
Okay, thank you for pinging. My headset at the time decided to turn off. I apologize.
Yeah, because I talked in the chat, on the mic, and I guess you couldn't hear that either. No worries.
That's why I have Teams up.
I got you.
Thank you. I will roll back to, was the metrics example finished?
Yeah, you went through that. It's just right when you turned on the new PowerPoint.
Okay,
Yep.
perfect. I'm going to pause quickly and turn off. I think my headset has an auto turn off feature, and I'm going to disable that. So let's disable that. So that shouldn't happen again. Thanks, Caleb. Just ping me if that happens again. Sorry, everyone, for that. We'll start from the top of the going to market slide. So by now we should have a first cut of our AI system software ready for deployment. However, software is only half of this. Artificial intelligence systems are just high performance computing systems with lipstick. And as any HPC engineer will know, your application is only as good as your hardware. One of the first things you'll want to consider is ensuring that you have a repeatable deployment process. With hardware, this means supply chain that is ready to deliver the goods when you need it to. This could be hardware in the cloud, an instance with a particular kind of GPU, or hardware from a vendor that is ready to be deployed on-prem within 24 hours, called drop shipping. The main takeaway is you don't want to maintain more SKUs than necessary. You don't want to have to rely on something brand new because your supply chain has run out. Now, choosing the right hardware to deploy en masse is really the crux here, and it's no easy task. An important aspect to consider is cost versus performance. Yes, sometimes with different ML models, we can achieve a higher accuracy using a larger AI model, like a Resonant 18 or a Resonant 101, a larger model producing a higher accuracy, as we can see on classic data sets like ImageNet. However, this will translate into a higher cost that a customer business may not be willing to pay, since we require a larger amount of compute. Additionally, deciding form factor depends on the application, as I talked about before, but let's dive deep into this particular piece. I like to split hardware into 3 categories: embedded edge, and data center. The embedded edge is smaller compute, smaller, that may live in an embedded device like a robot or an autonomous vehicle. Its small physical size translates into a smaller power envelope, since many devices are battery powered or have thermal concerns. The reasons you may choose an embedded system is typically for ultra low latency requirements, like what is found in an autonomous vehicle, or the system has no networking to back all the data to centralized compute system. So if you're out in the field, in a manufacturing facility, or on the farm. Often embedded systems will have direct access to sensors, allowing filtering. So used in a hybrid scenario, you may want to only backhaul certain pieces of data to the central server. So using embedded compute can be a good idea here. The real pain points of an embedded system are trying to update with a network connection. Sending USB stick or a disk in the mail is likely your best bet to do on-site updates, and the embedded systems have constrained compute due to the previously mentioned power consumption limit. Next is edge, or on-site compute. This could be pizza box sitting on a small rack in some closet, or a shoebox workstation system at someone's feet. Usually we're constrained to a 15 amp circuit, so only a certain amount of power can be leveraged, and how often someone's willing to let their office become, since these produce a fair bit of heat. You may go with this option if you don't have a reliable connection to a remote data center, or you have data governance or privacy concerns of moving your data over the network. You may also be conscious of network latency. So your local network latency will be much less than sending it to a remote compute or cloud center. The main pain points are very similar to the embedded edge. No internet connection means no remote updates, no remote monitoring, and another challenge is finding a place for noisy and hot computer away from dust and particles. Last but not least, definitely not least, is data center or cloud. Big racks, big power. This can translate into a public or private cloud, depending on what makes financial sense. You'll need a data center if you want to do big AI models. With the cloud, you'll be able to have access to on-demand scaling, which is good if your application has user spikes, such as we talked about before, social media ingestion or monitoring, or perhaps you run irregularly or on a fixed schedule. Your biggest pain points with the cloud is costs, particularly initial costs to set up and buy data center gear. While this can be offset by using the public cloud, if you compute with any great amount, the long-term cost of a cloud will be higher than the initial costs of building a data center. So while I can't tell you exactly what you want to use without a very focused one-on-one conversation, I do know what everyone needs to do, and that's optimize their system. There is a finite amount of compute that exists out there. It's a myth that you can always just use a larger amount of computing power to get your work done. And while you can always buy a larger computer, this doesn't work in practice. There are many reasons to optimize your AI models to run. We talked about this before, but the first and foremost, in my opinion, is cost. At some point, $1 million computer to drive a single car just doesn't make sense. You need to reduce your costs to be in the range of the business or a customer can afford. Also, larger profit margins are always a good thing for your business, and they're a good thing. Latency is another thing that you can't get around with larger compute. The law of diminishing returns will apply quickly when adding more compute, and in latency sensitive application, you may never reach the goal even with the largest computer on Earth. Finally, power consumption. Not only is it better for the environment, but optimization will lead to longer battery life. It also leads to less heat, which is critical for smaller form factors. So let's talk about the first thing that everyone wants to optimize, model inference. So like PyTorch or TensorFlow are built for training. Inference frameworks are built for deployment. You have generic frameworks like TorchScript and Onyx. But you also have device-specific frameworks like TensorRT and CoreML. Depending on the framework or format you choose, you gain different benefits. General frameworks like TensorFlow and PyTorch can be used for both inference and training. They offer great compatibility for any model architecture you can dream. As you move to inference-only frameworks, you start to lose some of that model layer compatibility and trade it for inference speed. Compiling models with used layers can start to really increase performance. And finally, compiling models with specific devices in mind provides the highest level optimization, utilizing the full power of the hardware available with custom kernels and other optimizations. This higher level of optimization comes at the cost of less compatibility with the latest models. Tried and true architectures like ResNet and BERT are easily convertible with pre-created functions, which I'll demonstrate in an example shortly, while new models may require custom C++ code to recreate the functionality of the new model architectures. In addition to using the model inference frameworks to optimize our AI models, we can also perform model optimizations that will lower latency and reduce memory footprint on a per model basis. So pruning or removing nodes of a model architecture may reduce latency, but will always reduce memory footprint. This can be really critical in smaller edge deployments. Quantization reduces the numeric precision of the computation used in the model calculation. Typically, models are trained at floating point 32, but can be reduced to floating point 16 or even floating point 8 or int8. This leverage with optimized hardware instructions like tensor cores for NVIDIA GPUs can significantly reduce computation time. And I will demonstrate this in a near example. Model compression or distillation uses a large network to train smaller network, distilling its knowledge and potentially leading to a higher accuracy, with all the benefits of using that smaller model. Sparse matrix operations have been shown in some cases to be an effective way of reducing computation. And overall, all these methods can be used individually or mixed and matched to optimize your AI workload. The critical thing you'll need to remember as you move through this process is that each method can and will impact your model's accuracy, and tests should be run at every possible moment to ensure that you're still meeting your accuracy requirements. So let's walk through a little bit of notebook example on different optimization techniques. So there's no need to restart this. So as I mentioned previously, it can be quite difficult without pre-done conversion functions like I showed in a previous example. You'll have to actually write custom C++ sometimes to get your model into a format like TensorRT or Onyx, but many models are already supported. So let's start this example. We'll walk through by creating a piece of data, a pre-processed image that we'll use to benchmark each of our methods. So first method, our first framework we'll talk about is PyTorch. PyTorch is a training framework. And as we can see, every time before, we're loading it in, and DM count is a VG19 base model, so a fairly common architecture. TorchScript is a way to serialize and just-in-time compile models. So we can create a dummy input here, pass it, and trace it with TorchScript to create a trace model, and then script it or compile it into a scripted model. Onyx is another framework we talked about, and it's built for representing all machine learning models. And PyTorch has a built-in export for this function, built-in export function for Onyx. Again, we create a dummy input. We pass in the original PyTorch model, the dummy input tell it to do a few optimizations, and this is an important one. We set the fact that there's a dynamic axis so we can control its batch size, and I'll show why that's important down a little bit later. Now the Onyx can be optimized even further using a tool called polygraphy, and polygraphy has been developed by the wonderful engineers at NVIDIA and is included with all the containers you can get from NVIDIA's NGC container registry. And one of the functions we're going to use is to sanitize the model, and this folds the model, folds the contents into other nodes, reducing the size of the network and can potentially give a speed up. So it's just a simple command here to search and sanitize the model Onyx, and we'll create a model simplified and folded Onyx file. So we can see as we scroll down here, 9 nodes were folded, which reduces the model size. Finally, TensorRT, which is a framework for creating very highly optimized models for inferencing for NVIDIA GPUs. And we're going to use the polygraphy tool as we did above. We're going to polygraphy convert the simplified Onyx to TensorRT into an engine file, and we're going to specify. See here, we're going to specify the minimum shapes, the optimum shapes, and the maximum shapes, specifying that a batch size of 8 is going to be the largest we'll use with the model. So measuring the latency difference. Here, I set up a simple time it sort of set of scripts where we run through and process the different latencies, and we're going to record the minimum latency for plotting at the very end here. So I'm not running these pieces down because they do take some amount of time. I have it set for 20 iterations, and it takes a fair bit of time to get through. So I just wanted to make sure that I get it done in a timely fashion. So I'm just going to scroll down here to the place where I plot. And so I'm plotting the raw PyTorch, TorchScript, Onyx, and TensorRT models and their latencies. So the latency of DM count across different models. Here we can see the raw PyTorch and TorchScript models are operating in the 34 millisecond range, while the Onyx and TensorRT are much quicker, operating all the way down at the 26 millisecond range for a single inference. We can also see the batch size, how increasing the batch size on a per image basis will get a lower computation time, showing that we are getting a better throughput efficiency. And I'll bring that up a bit more in a second. I wanted to give one more example. Polygraphy has an excellent tool for converting the Onyx models to TensorRT with floating point 16 enabled. It's basically something that you can just turn on. You just pass this one piece and you have it in floating point 16. Now you need to verify that your conversions are still within the accuracy requirement that you want. So that's something to be sure of, but typically your rule of thumb with a floating point 16 quantization is about 0.1% error increase. So if your MAP is 39%, now you have a 38.9% MAP. That's typical rule of thumb for a computer vision model. Finally, we're going to instantiate the model for floating point 16 for TensorRT and run it, and we'll note the latencies again like we did last time. Again, we're going to also do the torch script and cut the inference in half, cut the precision in half using a .half function, move it to floating point 16, and then we're going to print out the pretty graph that shows that using quantization will often greatly reduce latencies even further, showing that we're going from with TensorRT, 23 milliseconds all the way down to about 7 milliseconds at the batch size 1. So that's quite a significant speed up just from enabling a flag and leveraging the tensor cores that are already on your GPU. Another note here, which we'll dive into a little bit more on the slides, but latency and throughput, talking about how as we increase our batch size, the latency does increase, but the efficiencies we see can grow. And so with that, I'm going to roll back to our slides and continue to talk about latency versus throughput. So showing that we can optimize the PyTorch model further, we need to talk about how we can use this optimized model to meet our latency and throughput requirements. A trade-off between the throughput and latency of an AI model can be controlled by adjusting the batch size passed to the model. If we wish to have maximum latency, we simply clamp the maximum batch size. The bigger the batch size, the better we utilize the hardware. If we have a larger device and a small model, we will see a better scaling effect. So in that graph, we'll see that the latency is linear going up and no real dip. Throughput, pardon me, total latency going up, the latency per image goes down. So there's no real effect here. But if we have a large model in a small compute device, we'll often have no effect, while a large compute device in a small model will see a benefit by using a higher batch size. Now, if you need to reduce latency overall or generally optimize your system, you shouldn't only look at the model's inference. The through pre and post processing, the data ingestion, all add to it, since latency is end to end. If the compute hardware has to work at doing pre-processing and inference at the same time, lowering the computational load of one will speed up the other, not to mention lower end-to-end latency. So let's say we have a single task running sequentially in a single thread. We have our latency and we have our throughput. So when we move to using multiple threads, our throughput goes up since our tasks are parallelized. We can accomplish more inference and devices are sitting less idle. However, our latency hasn't gotten any better. It still takes the same amount of time to get a result. So assuming we already optimized our model to maximum, our next best bet is to look at optimizing our pre and post processing. Firstly, reducing data transfer between host memory and the GPU can really improve performance. Using the same device for pre and post processing as inference will reduce the bus's I/O and less transferring between compute devices. If you're using Python, like most AI applications do, compiling your code can really reduce computation time. Moving to C++ or C Python, Numba, etc., they're all good opportunities for improvement, since compiling your code will reduce the time taken. Most critically, are you using the right hardware for your pre or post processing? For instance, GPUs have accelerated decoding units for image or video and audio, while you have accelerated computing instructions like AVX for vector calls or tensor cores. They all can be used and leveraged to accelerate your tasks. So let's just drive this point really home with another quick example. The last notebook example I have. So let's simply start with the reduced data moment. So we're going to declare just a random random data of size 4 images of a RGB image of 800 by 1280, or about a 720p image. So we're going to declare that, and then we're going to move it, moving it from CUDA, which is the GPU, and back to the CPU. And we can see it actually takes, if our inference took about if we optimize our inference the whole way to about 7 milliseconds, we're going to reduce we can reduce our latency further by getting rid of those moving data to and from the GPU if we can keep it on the GPU longer. So next, we can look at compiling pre and post processing. So as we did up above, we have a resized image, and then we're going to pre-process this image with the same function as we had in previous examples. We're going to time it, and we're going to find that it takes, I believe, about 8 milliseconds. Yes, 8 milliseconds to run the pre-processing. So Numba is a tool which we can take NumPy code and we can actually compile it into a function to be used that is much more efficient. So we're going to take it and then run it. And you'll notice compiling it, we can reduce down to 4.61 milliseconds. So that's nearly a 50% reduction in speed. So that's quite a significant lowering in processing speed. And it's nothing to ignore when you're trying to reduce latency as much as you can. So just remember when you're doing your full optimization, not to just look at the model inference, but also look at the pieces before and after the model inference. Another tool like NVIDIA's DALI can also not only compile the instructions, but also keep the instructions running solely on the GPU, so reducing both the data movement as well as keeping the pre and post processing computation time low. Going back to the slides, and now that we've kind of going back to the diagram from earlier, we talked about how we can optimize the pre-post times, and now since we're lowering the computation time, we not only see a latency reduction, but also another overall increase in throughput. So again, hammering the point home, always remember to optimize. So there is a whole other class of AI models out there, models that are so large that a single device isn't enough to compute the results. Large language models are the best examples of large models today. Foundational models like GPT-3, Bloom, and Megatron are so big, it's hard to quantify. Often the number of parameters are so large that they're in the billions. So how big is 530 billion parameters? Well, it ends up being about 4 terabytes of FP32 memory. 4 terabytes of memory at floating point 32 precision. So optimization like the ones we spoke about previously is a must for models at this size. Thankfully, there are tools that are built for these purposes. Tools like Faster Transformer and DeepSpeed implement frameworks for running these models across multiple compute devices. Multi-device inference is critical for achieving any reasonable performance with these models, splitting the memory across multiple devices. So tensor parallelism is one way of splitting these models across devices. It reduces latency, but requires a very fast interconnect between devices, since we have to exchange the results after every layer moving through the network. Pipeline parallelism only communicates once with the next device in the pipeline, but this only increases overall throughput. So depending on your application, you'll be looking at implementing tensor parallelism, pipeline parallelism, or both with these large models. The biggest tip I want to instill with this is that you only should process the data that you need to. So a few examples of this are, first, a computer vision use case. Moving on a sidewalk is much slower than on a highway. You don't need to process a full 30 frames per second if you're walking on the sidewalk. But if you're on the highway, you may want to even process more frames, 30, 60 frames per second, since less frames means more frames mean we can react to things faster, but if we don't need to use them, the less frames we process means we have a lower throughput requirement. If you're doing sentiment analysis for social media, you could even look at ignoring single word responses, since the sentiment of single words could become a lookup table. And to take that a step further, creating a cache or lookup table for commonly said phrases, short phrases that are well understood as a positive or negative sentiment. Overall, the less computation you're spending doing these sentiments, the better. Finally, with defect detection and manufacturing, if you're taking a picture of an image, if you're taking let's say a piece of wood coming along the conveyor belt, if you're taking a square image, are there parts of it that can be cropped? There's no need to process the parts that aren't the parts of the image that aren't looking at the piece of interest. So don't waste your time computing the pixels. The less pixels to compute, the less time the model inference will take. So into the final stages. Hopefully by this stage, your deployment will meet requirements to work in the field. However, your work isn't done. This is an iterative process. So scaling, whether based on user demand or with the development of new products, is always on the horizon. You want to make sure you don't run out of compute. This is where an orchestration tool like Kubernetes comes in handy. In the cloud, you can simply spin up more compute as needed, but on edge, mesh computing can be leveraged. If another robot is sitting on the charger, have it do some long-term forecasting for all the robots that are out in the field, since it's just sitting there and charging. The metrics we add at the beginning of this deployment example can be used here too. You can look at queue latency or the number of active users in your system to scale your services based on the demand or how long the responses are taking to come back from the model. So having our computer scale is one thing, but how can we make our AI models better, faster, stronger? New model architectures are always coming out. Browsing websites like Hacker News or Papers with Code, you'll also see new models that are having the same accuracy of what you currently implemented with a lower latency or better accuracy with the same speed. While you can rely on publishing in the field publishing new results for you to use, you could also use enough compute to explore your models with AutoML. So have a AutoML uses a computer to algorithmically explore different combinations of hyperparameters and layer types and even the data that you may use, allowing you to kind of have your models do the work for you in behind the scenes. Another surefire way of improving your model accuracy is gathering new data. Getting the invaluable feedback from the field can inform new examples that you need to capture. Maybe you never experienced users holding an umbrella, and suddenly you have 1,000 umbrellas on a rainy day that you need to account for. If getting new data is hard for you, generating new synthetic data is a great way of overcoming this, and it can help grow your data sets and increase your system's robustness. Just really hammering this point home, your field data is your friend. Customer feedback will tell you if your model is giving the wrong outputs or isn't fast enough, and live monitoring will hopefully tell you that it's too slow, people aren't using it, your system's having errors before the customer tells you. The MLOps cycle is really a big part of this. So when we hook up our metrics and customer feedback into our cycle, we can automatically create new models based on the customer feedback and the monitoring. And there's been hundreds of articles on MLOps like cycles in the previous little bit, and many tools to create them. And several works have been already presented at this conference. So I'll leave these extra details to these other sources to talk about, but I have another point before I actually wrap this workshop. And so the thing is that each time you deploy an AI system, it will get easier and easier. Your requirements will be better understood from the get-go. You should have lessons learned fresh in your mind. You need to remember that each time you do this, you should be building with reuse in mind. Generalize what you can because you don't know what your stakeholders are going to ask for next. I know this from experience. Finally, centralize your compute. So optimize the AI workloads across all of your clusters. So as you add more models to run, this will become more and more important. Schedule your infrequent jobs when possible. Don't run them at the same time. There's no point using more compute in a single spike than balancing over the course of a day. The more applications you add that leverage AI systems, the more scalable you'll be able to architect your central infrastructure. This is equally important with large data systems as well as edge space systems. And here's an example again showing that having just a visual example saying that you can load in models in and out of your inference server depending on what your applications need. So to summarize, work as one team to get the AI models into the field. Data scientists, back engineers, even UI designers are all on the same team. Look at every part of your pipeline to optimize. Don't assume it's just inference. Yeah, I was just going to put for this part like metrics, but more succinctly, specifically the data you collect from the field will be informing every decision you make. make sure to take it seriously and record it and ingest it. And most importantly, ML system building is an iterative process. You will not get it right the first time. I never have. Assuming that AI system building, if you're not going to get it right the first time, is better. It's an iterative process. The industry doesn't even have the process down yet. No one is probably doing this right the first time. So with that, I'm going to wrap this and hopefully open up the floor to questions and answers. Thank you so much for listening in. And if you have no question and answers now, feel free to add me on LinkedIn and ping me with a question if it comes to your mind just after this presentation. Caleb, do we have any questions in the chat?
Yep. We just had one come in. It was a great presentation, very thorough. So we didn't have many during the presentation. We had one come in, and the question is, what are some ways to tell when a model like Mask RCNN is performing poorly in production?
That's a great question. I see Ken published it here. So Ken, that's something that I can personally relate to as Mask RCNN. But one of the ways to look at it, and we talked about this briefly, is recording the average class accuracies you may be seeing. So if you have an accuracy of, let's say, 90% most of the time, and you occasionally see a dip in class accuracy, so let's say you're seeing 90s, 80s, and suddenly you get a class accuracy of 30 or even 40, you can look at that dip as it's doing poorly because it's seen something it hasn't recognized before. Another good way of performing poorly is actually introducing some sort of feedback loop to the customer. So creating like a user interface saying this wasn't accurate or this wasn't great, and then capturing all that data together and passing it back to your data science team. If that's something you can build into your system's workflow, is another excellent way of doing it. I hope that answers your question, Ken. I just saw, oh great. I just saw another question. Yes, I'll be sharing the presentation itself. If you hold on to that GitHub link, and I'll put that GitHub link back on. I think I had it up here. Here, I'll just skip back to very top. So this link here, I will be publishing the slides and my speaker notes along with it, along with all the code. So you can access it whenever you have a chance. Any other questions from the audience? I think this is there may hopefully I gave everyone something to think about at the very least. But I'm going to go with the silent chat as everyone else has moved on. So thank you everyone for attending. Again, if you have any, you should get a copy of this presentation as well. Great. Thank you everyone for attending. I'll wrap it from here. Please reach out if you have any questions, and thank you, Caleb, for moderating the chat there and pinging me when my audio died. Take care, everyone.